In this lecture, we will discuss some questions related to the basic signal symbol, steps, and ramp. And we will verify 2-3 cases. First problem, here we need to verify the relationship del of n is equal to u of n minus u of n minus 1. The del of n means it's a discrete time unit step impulse signal. So this is impulse signal del of n is equal to 1 for n is equal to 0 and 0 for n not equal to 0. So if you draw the discrete time sequence, then at n is equal to 0 the function magnitude is 1. Okay, so this is a discrete time sequence del of n. Okay, now u of n means u of n is equal to 1 for n greater than or equal to 0 and 0 for n less than 0. So if you draw the signal u of n for n greater than or equal to 0, the function magnitude is 1. So from this particular point the function magnitude is 1, and it will continue like this. And for minus values of n or negative values of n, that is minus 1, minus 2, minus 3, minus etc., the function magnitude is 0. That is u of n. Now we need to define u of n minus 1. That is the shifted version of the step signal. U of n minus 1 is equal to 1 for n minus 1 greater than or equal to 0, because in this particular case when n is greater than or equal to 0, the function magnitude is 1. In place of n, here it is n minus 1, so we'll write n minus 1. So if you rearrange this, you can write n greater than or equal to 1, and 0 for n minus 1 less than 0, or you can write n less than 1. So here is a point n, and this is a value n is equal to 1, and for n greater than or equal to 1, the function magnitude is 1. So from 1 onwards, 1, 2, 3, 4, 5, 6, etc., is having magnitude is equal to 1. And for n less than 1 means 0, minus 1, minus 2, minus 3, minus 4, etc., the function magnitude is 0. So this is your u of n minus 1, that is a shifted step signal. And now we need to subtract u of n minus 1 from u of n. So this is a waveform u of n. So we need to perform, this is u of n and this is u of n minus 1. And if you subtract these two signal, okay, you can see that this is n, and here it is n is equal to 0. At n is equal to 0, uh, u of n signal magnitude is 1, and here it is 0. So 1 minus 0, you will get 1. So at this particular point you will get 1, and at 1, if you observe the waveform, here it is 1 and u of n minus 1 is also 1, so you will get 0. And 2, again you will get 0. 3, again you will get 0. 4, and for negative values of n, for minus 1, minus 2, minus 3, etc., again you will get 0. So u of n minus u of n minus 1 is having non-zero magnitude only at n is equal to 0, so which is similar to del of n. So graphically we can prove this particular, or graphically we can verify this particular relationship. That is del of n is equal to u of n minus u of n minus 1. Now we'll discuss another question. Here the step signal u of n is given by sigma k is equal to minus infinity to n del of k. So del of n means it's a discrete time sequence which is equal to 1 for n is equal to 0 and 0 for n not equal to 0. So if you draw the discrete time sequence, it will be like this. It's a discrete time sequence for n, and the signal is having non-zero magnitude only at n is equal to 0. And for all other values, the function magnitude is 0. That is del of n. Okay. Now, here it is given u of n. That is a step signal we need to plot, and which is given by summation k is equal to minus infinity to n del of k. So we can try how we can find out the u of, for example, we need to draw the signal u of n, and first n is equal to 0. So when n is equal to 0, it becomes u of 0. We can find out the value at n is equal to 0. And the equation becomes k is equal to minus infinity to 0 and del of k. So in this particular expression, we need to substitute the values of k. So we'll start from del of minus k, sorry, in place of k we'll put minus infinity, etc., etc. You'll write del of minus 2, del of minus 1 plus del of 0 plus del of 1. Sorry, in this particular case we don't write to del of 1, because k is ranging from minus infinity to 0. So you need to write up to del of 0. And we know that the signal del of n is having a non-zero magnitude only at n is equal to 0. That is, del of 0 is equal to 1. So in this particular case, del of 0 is 1, and for all other values, when n not equal to 0, the function magnitude is 0. So you'll get 0, 0, 0, etc. So the final result will be 1. So when n is equal to 0, you got u of 0 is equal to 1. So you can mark 1 here. Okay. Now we need to find out u of 1. That is for n is equal to 1. If n is equal to 1, your summation becomes k is equal to minus infinity to 1 del of k. And if you expand this, it becomes del of minus infinity, etc., etc., because k is starting from minus infinity up to 1. So del of minus 1 plus etc., del of 0, and k ranges from minus infinity to 1. So you can write up to del of 1. And if you observe this particular term, we know that del of 0 is equal to 1, and all other values of n, the del of n function is 0. So all other values are 0. Here also del of 1 is also 0. So finally you'll get again 1. So when you calculate the value at n is equal to 1, you will again get 1. Okay, that is u of 1 is equal to 1. Now we can try and for a value which is n is equal to minus 1. So when it is minus 1, it becomes u of my equation becomes u of minus 1, and k ranging from minus infinity to minus 1 del of k. Okay. And if you substitute the values of k, it becomes del of minus infinity onwards, and assume that del of minus 2 plus del of minus 1. If you observe, when n is equal to minus 1, there is no del of 0 term. Okay, because del of minus 2 is 0, del of minus 1 is 0, and all other values are 0. Only del of 0 is 1. But in this particular expression, there is no del of 0, because the limit is ranging from minus infinity to minus 1. So the final answer will be 0. So here it is 0. And if you take any negative value, the function magnitude is 0 for any value of n. If you choose n is equal to minus 2, again you will get, when n is equal to minus 2, again you will get up the same expression only up to del of minus 2. So u of minus 2 is again 0. And similarly, when you take any positive value for n is equal to 1, 2, 3, etc., you will get only one non-zero magnitude, that is del of 0, and all other values are 0. So when you calculate 2, again 3, 4, 5, you will get 1 1 1 etc. So which is equivalent to your step signal. So by using this graphical method, you can verify this particular stuff. So this is another relationship between del of n and u of n. Here del of n is given as a shifted version of the signal. So again del of n is equal to 1 for n is equal to 0 and 0 for n not equal to 0. Okay, that is if you draw this waveform at n is equal to 0, the function magnitude is 1, that is del of n. And all other values for 1, 2, 3 or minus 1, minus 2 etc., the function magnitude is 0. Now in this particular expression we need to find out u of n. So we can find out u of n by using this equation, and for n is equal to 0, at this particular point we need to find out the magnitude of the function. So we can write u of 0, it becomes k is equal to 0 to infinity del of n is equal to 0, so you can write 0 minus k. Okay, 0 minus k means now we need to apply k limit k ranging from 0 to infinity. So you can write del of 0 minus 0 plus del of 0 minus 1 plus del of 0 minus 2 etc etc up to infinity. But we know that this is del of 0 and next term is del of minus 1, del of minus 2 etc. Okay, and we know that del of n is equal to 0 is equal to 1 only for n is equal to 0, that is del of 0 is equal to 1. So here you'll get 1 and all other terms are 0. So at n is equal to 0 you will get 1. Now we can try n is equal to 1. When n is equal to 1, u of 1, which is given by the equation k is equal to 0 to infinity del of 1 minus k. Okay, because n is equal to 1. And if you expand this particular expression by substituting k is equal to 0, you will get del of 1 minus 0 plus del of 1 minus 1 plus del of 1 minus 2 plus etc. Now you can write this is del of 1 and this is del of 0 and this is del of minus 1 plus etc. So we know that only del of 0 is equal to 1 and all other values are 0. Okay, so finally you will get 1. So when n is equal to 1, the function magnitude is 1. Now we can try n is equal to 2. So when n is equal to 2, you will get the exactly a similar expression, or here another term will be there, that is del of 2. Okay, so but if you expand, there is only non-zero magnitude, that is 1. So you will get 1. Now similarly, if you observe del of n is equal to minus 1, that is u of minus 1. So the expression becomes k is equal to 0 to infinity del of in place of n you can substitute minus 1 and k. Now if you substitute the values of k, the expression becomes del of minus 1 minus 0 del of minus 1 minus 1 plus del of minus 1 minus 2 etc, and you plus etc. And if you observe this particular expression, as always negative values, del of minus 1, del of minus 2, del of minus 3 etc. So all these values are 0 0 etc. So finally you will get 0. For negative values of n, you will get the function magnitude is equal to 0, and it will be same for any negative value of n. And for positive values of n, you will get 1 1 1 etc. So the given expression is also correct. So we can write u of n is equal to sigma k is equal to 0 to infinity del of n minus k. Okay. So I can express the step signal in terms of del of n. Similarly, another expression we already discussed, step signal can be expressed as sigma k is equal to uh, minus infinity to infinity del of k. So I can express step signal in terms of impulse.